of the lectures. So first, I'm going to cover some problems available. Problem with the current deep learnings in respect to the reasoning process, and then explain a bit about the neural system theories, and then cover a bit about the existing idea that may be available for the high-level reasoning, and then cover a bit about the very important topic of reasoning, which is still underdeveloped, is co-theory of mind. Let me start by explaining why we got it here. Is that deep learning, as we've seen, is very fantastic in terms of application for certain domain where you have a lot of data and computations. But looking deep into it, it looked like deep learning is very good at interpolating. Right? So it means that it tried to connect between the data point and find the reason in between, so that if the future data point, future task or data points or unseen data point fall into the between its reason, then we're gonna have very good accuracies. Right? The downside of that is that it's very data hungry, because we need to cover all possible variations, the future variation that we're gonna imagine, and smooth everything out, so that whenever the future data happen or task or query happens, we already have some sort of smoothness, right? And it would be able to answer it correctly. But that is very strong assumption, that we assume that the data doesn't change over time, right? But in reality, data change very quickly over time, and in over space as well. And if a different context, we would have the very different data distributions, and all the assumptions become wrong. And it is very profound in reasoning, because every single question is new, right? So you may not have not seen the question before, but we should be able to answer it. Right? That's the basic requirement for the thing called the systematic generalizations. So what it means is that we should be able to work nicely to the novel combinations, even if that combination is never seen before and have almost zero probability of being happen in the training data. And second part is that deep learning is kind of lacking some reasoning capabilities that are perceivable to human. Right? For example, it doesn't have very natural mechanism to incorporate the prior knowledge, like common sense, for example. Right? Let's say if we have a concept of the room, then common sense tells us that the room must have a door, and the door should have the handle of some sort, so that we can open it, or at least some way, a button or some way to open it. Right? But right now, we don't have very good way to incorporate this kind of knowledge into the deep learning models. And the deep learning by nature was designed for the correlations. Right? You try to correlate the input and output. It doesn't have very good mechanism to infer the causalities between events. Right? Something cause something. Right? So putting all together, it looked like the deep learning going to have a big problem, and already is. That they going to have a trust issue with humans, because in critical domain like healthcare, for example, who's going to trust a black box model that cannot think in a similar way that human thinks? Right? There's no way to verify what model doing implicitly. Right? And of course, to be fair to deep learning, those problems are not unique to deep learning. It's a problem for all the statistical systems, because that's the nature of statistical learning. Right? So one of the problems I mentioned earlier, is a concept of systematic generalizations. So it means that it refers the ability to work with the new combinations, even if this combination have zero probability in training data, because the nature of statistical model, if the data have no support, then we have the zero probabilities, and by theory we can't do anything with that, right? So, but human doesn't have that problems. For example, if we understand the concept, the sentence that John loved Mary, then we automatically know that the concept of Mary loves John is perceivable. Right? It's nothing really new, because we quickly infer that some actors love some the other actors, right? Regardless of who the names are. Right? But machine learning, if we put it the new combination like this, it's gonna fail, right? Unless we design it in such a way that it maybe in this way it does some sort of regular expression, but currently they are not designed generally for this. Of course, this problem is not very new. It has been argued, for a long time ago, at least as early as in 1988 by Fodor and Felicien. So they argue that there's no way neural networks, or what they call the connectionist model by the term, can perform systematic generations because of the second set limitations. Right? But of course, people who are doing neural networks think differently, saying that yes, it's possible to do the systematic generation, provided that we give enough flexibility and enough care about the design models, right? But of course, sin has been unsolved problem, and the modern research must research is needed. For example, we're dealing with syntax, in concept of indirections, multiple data sets, how to measure the generation capability. So those kind of things are still very in a very early days, still unsolved, but there's some good concrete progress out there. So if you're keen, one of the early paper, not very early, but recent paper is a paper published in I think IJCAI 2019, asking question is that what's required and can it be learned? So they did a bit of experiments showing that it's very hard for the current model to do so. But there must be some hope that we can design the neural network in certain ways so that it can perform systematic generalizations. So the other problem is known as the out distribution problems. So it means that the assumption about data, stationary assumption or fixed distributions doesn't hold anymore, because imagine that AI in the future going to live with human and have any long-term relationship with human, then a lot of things happen, right, during the lifelong relationships, and then people grow, right, people change, and also it's a life-wise situation where every single day we change in multiple contexts very quickly, answering the call, cooking, going out shopping or going to the gym and everything else. It's some sort of context switch, right? And the problem is that even the contexts are changing as well. We don't have a fixed set of contexts to switch, but the context itself, the definition and the nature are changing as well. So how to handle this problem is still very, very open, very difficult. And it looked like we did some sort of continuous learning, so that the system continually learn and change itself. And the problem is that we may face the trouble of known as the catastrophic forgetting, meaning that what we new thing we learn, we're going to forget the old thing we already learned. So it's not very desirable. So how to handle these things is still very active in research. Right. So the next part, I'm going to explain a bit about the what people call the dual system theories or dual process theories. So this concept has been there in cognitive science for a while, and it's been popularized by Daniel Kahneman in his best-selling book Thinking Fast and Slow. And in his book, he explained that there are two mechanisms for human to think. One is fast thinking, and where we don't need to think that much, we just recognize it instantly without much effort. Another mode of thinking is that it's called slow thinking, where we collect evidence, we slowly changing the evidence together, refute argument and other things. So at the end of the day, we got some answer. So that the slow thinking capability is also known in the cognitive science as a system 2, right? So the nature of system 2 is very different from system 1. So system 1 is pretty much what we have today in machine learning. That's a system that very quickly maps the input into the output. But system 2 is quite different because it doesn't need to stick to the real world at all. So it can decouple itself from the representations, right? And it can hold the hypothetical thoughts, so that it allows us to do the mental travel, think about the future and the past, and think about other people and think about our own thinking, right? This capability is very different from what we have today in machine learning. And as I said, it's not a fast process. It's slow and it's deliberative, and most of the time it's require consciousness, right? Of course, consciousness is a big field that very few people have a good thing to say, but we know from our experience that when we put effort into thinking, we require some sort of consciousness. It doesn't happen instantly. It doesn't happen by itself. It happens with some effort, right? And then by that nature, we need some sort of the working memory to store information, to retrieve certain facts, or compare on other operations that we need for the reasoning process. But evidence so far saying that the size of working memory is important, but the ability to control it is more important, right? So that related to the concept of attention that we mentioned earlier. So it looked like the attention, it's a very powerful concept, right? The problem is that the concept system 1 and system 2 are not uniquely defined, right? So there's huge difference between the uses of the concept by different people in the past 30 or 40 years or so, right? Some agree on the definitions, are not. Some are freely available in different way. So here's a table that being listed, seeing that actually people don't talk about exactly the same thing, even though they tend to agree that system 1 is automatic, reflective is simple. Reflexive is simple. System 2, on the other hand, is not automatic. It's highly controlled and require deep kind of cognitive power, and it's rational. It's explicit and requires some sort of conscious effort to be able to do so. When we talk about system 2, and that be aware that they're not the same thing when the different authors are talking about it. Right? It's good for us to be aware of those two differences. Another question is that when you talk about system 2, it's not really a single system. They're going to do everything, right? It looked like we have the multiple subprocesses within it. So here, at least here's one of the model that Stanovic proposed about 10 years ago. That he thinks that system 2 may have 2 components at least. One top component is called reflective mind. It's a place where we initiate all the computations, right? And we control the thinking process. And the other sub-process is called the algorithmic process. When we make use of certain rules or computation power to do certain things, that together from the system 1, system 2 in the what people think about today. But in the literature, come to machine learning literature, it doesn't seem like people talk about this too much. But I'm giving it here as a way for us to think about what's next. Some food for thought. Right? So given all of those concepts, why still very not well defined yet, what we can do is here's one possible architectures that we can employ that kind of thinking. So in these architectures, we would have the inputs, perceptions, to either is vision or speech or other kind of perceptions, sensory. So we have the system one, multiple system one running in parallel to make sense of those data. Basically, is to compute certain outputs or represent the data in a certain way. And that pretty much our deep learning system today are doing. And then we have system two, which make use of the processing of the system one, and try to put a higher order processing into it, right? And it tends to be sequential process, linking all the evidence and predict it and think together. And it's not a parallel, it's not simple. It have to be slow and just sequential. And both the subsystems are using memory as a basic mechanism to store information. Either information could be the set of facts, the nature of semantics of the concept or linguistics, or just a set of events and relations that are being collected, or it could be the very fluid, like a working space for the thinking, right? So memory is a big chunk of system that have multiple components and serving a different purposes. And all the components together may be linked to and serving as a input for another kind of high-level reasoning is called a theory of mind. So where a system that have the theory about the other systems, that thinking about what other people thinking, and maybe thinking about what other thinking about this system is thinking. So it's kind of recursive mental travel in that sense. And of course, this one is still very early days. I want to talk about it a little bit at the end of this lecture. Right. So what are we having in store for system 2, given the requirement that we want to need a kind of high-level system that is not just doing the very simple pattern recognition, but doing a high-level thought. What are these in store? So one of the thing that probably we needed is a kind of obvious that we need the object concept binding. So what I mean is that we will have the perception, but the perception is in different semantic space. So then you have the concepts like linguistic concepts, and in different space, and for any reasoning to happen that related to the real world, we need to find a way to bind those objects, perception objects, and the concept, high-level object, high-level concept together, right? So then we can do a reasoning, like a grounding our high-level reasoning into the realities, right? So here's one of examples that one of our co-author here, co-presenter here, Tao Lei, was a first author. He designed an architecture called LogNet. So every step of reasoning to be able to build relationship between the perception objects. It query the linguistic concept and try to find a binding between the linguistic concept to the correct visual objects. And that process, it's linked and like similarly link the binding and the relational reasoning between objects, so that we have the new the state of the object keep refined over time, so that at the last step we can have the answers emerging from those subprocess. For those who are keen to read more about binding, there's a very good paper by student of Eugen Spinoza. It's called "On the Binding Properties of the Neural Networks," and it discuss very wide range of concept of binding, not just object concept binding that I mentioned here, and a very good way to think about how to move, how to make big move in the neural networks, in the next 10 or 5 years or so. So here's one example of the object concept binding. So we have a question have a question here on the top row. We have the question like, is the color of the big metal object it's the same as the last metal cube? So in order to do so, we have multiple steps of linking object together to bind the concept to the object. So the binding is shown as a kind of blue greenish link between the words and the objects, and the relation between the object in the context of the question. It's a link to the red line in the picture here. Right. So another concept of is attention and interaction. So I mentioned earlier, attention is a way to focus, right? So we can focus on a relevant piece of things. So on the picture on the right, you see that the vision system as a way, our human vision system as a way to focus on the relevant part. For example, on the facial part of the babies and some keywords in the text. But in this real system, we might have, we might focus on multiple things, not just the item. We can also focus on a relation or even the model or subprogram. If we think about designing the program on the flight, given the query. So when a piece of information we attend to is not the information itself, but the pointer to others, we have the concept of interactions. And this is very powerful way to generalize into different implementations, because the pointers can, pointer can be very different from the values, right? So if the pointer's content change, but the values, which is the name of the item, doesn't change, then we can generalize system into the new domain when the kind of relation doesn't change, or kind of name doesn't change, but the input nature would change, right? So that's a very powerful way to have those generalizations to the concept of interactions, right? But another thing is that the kind of attention is still very expensive to compute, because we need to scan all possible items and then compute the probability of each item in the system. But maybe in the better way to think about is we need a zooming in mechanism, so that we first compute very coarse attention mechanism, attention for the big superset or reason, and then zooming in into more detail of the part. So for that, you might save a lot of computation and be more accurate rather than the current practice that we're doing, which is basically doing softmax over the all possible items in the set. Another thing we have installed, it's a way to do the iterative message passing in the belief progression, as I mentioned earlier. So on the right-hand side, the example of the message passing, for example, we want to send a message from node I to node J. To be able to do so, we connect all the evidence all the messages coming to the node I, summing over the opposite value of the variable I, and then sending that message to the node J. Okay? So that's a way to do the iterative inference in the belief progressions. What it does is that it updates the belief of the unobserved variable given the evidence that we have in the observed variables. And then, as mentioned earlier, it's known before that it's a way to minimize the BT free energies. Right? So the question is that does belief progression qualify as a candidate for system 2? It looked like it's iterative. It have state refinement capabilities, but truly is that really mechanism for system 2? We still don't know, right? But it had some feature of system 2 already. Another mechanism we have installed right now is a message passing for neural graphs. Actually, we already have that in the sense of the convolutional neural networks. When we send implicitly send the message between the pixels, then we can generalize that concept into the GCN, which stands for the graph convolutional net. In the sense, it's sending information through the connections. but just assume very specific form and doesn't have the concept of relations. It has the concept of link, but doesn't have concept of relations. We can generalize that concept into multiple relation model. Then you have to generalize the concept of message passing, at which every single step we send the message from the node A to node B, and then the node receiving node would gonna collect all of the evidence from the neighboring nodes, adjusting to the relationship between them, and then refining its own state and keep doing and resending that message back to the neighbor. So the entire process is kind of recurrent process itself, and over time we have the state refinements happening. And this is a very good candidate for questionnaire links. And as mentioned earlier, transformer actually doing similar thing because it keeps refining relationship between items and also sending message through self-density mechanisms. And another candidate for the system 2 is that we have the concept of modular recurrences. So one of the interesting papers called RIM, stands for the recurrent independent mechanisms. So it assumed that the entire system is recurrent, and at every single steps, we had a set of module that are sparsely activated, and those sparse activated module gonna pick up only few bits of the input to process at the time. And those modules communicate sparsely over time to self-attention mechanisms. So that is a way to think to design a sort of program construction in a way, or some sort of the predictive training in a way through the concept of the modules, like a sparse module activations. Right. The other concept we have installed right now is called the relation memory. So my colleague here, Hưng Lê, is going to talk about it more detail in his part about memory. So I'll give you the hint here is that instead of having a single memory for everything, we have the separate memory for item and a separate memory for relations. And the memory for relation is going to store the the connection between item, even those items are distant apart, right? So if you have the entire system running recurrently, we have very powerful way to do the relational reasoning over the long period of time, and in very efficient way. And then moving forward, it will have the a way to build the program on the fly through the concept of the neural store program memory. So instead of storing the item or relation in memory, you store the weight of the neural itself in the memories. And then whenever we need it, we're going to combine those weight together and to produce a new neural networks. Right? So we can build the neural networks on the fly whenever we need it. Right? So my colleague Hưng Lê is going to talk about it in his part later. The next thing available in store right now is I have a very good mechanism to analyze data with syntax. So it fit into the problem with the linguistics queries or inputs. So we can, in theory, we can analyze syntax, and through the nature of the composability of the syntax, we have very good way to improve the systematic generalizations, right? By using the same syntax but with different words at the leaf of the syntax tree. Here I'm giving a very simple test that trying to prove the concept that actually system 2 can be separated from system 1, and they are just simple dynamics connection between the two may serve as a good candidate for reasoning. So given that we desire a simple system that have the feature attraction for video and then link to the magnet that I mentioned earlier as a candidate for system 2, even though magnet wasn't designed for system 2 per se, but let's assume that we can have a system that doesn't need doesn't depend too much on the nature of the input. and it can do the iterative refinement independently of the nature input. So we're going to connect system 1, which is a feature tracks, and system 2 is about reasoning together. And system 1 is pretty much a way to compute the dependency between the frame in the video. And system 2 is, as I mentioned, is a magnet, is a candidate, even though we can argue that it's not a perfect candidate for system 2. But it's for now, I assume that it serves as a good candidate because it doesn't depending on it doesn't have requirement for the nature of the input, as long as we can have a set of input and set of query items, and then we can do reasoning on top of it. So that part is some existing idea of or candidate for system 2. The research still going on, but let's hope that there come more important ideas coming up. For the last part of this lecture, I'm gonna quickly mention a bit about the concept of high-level concept of reasoning is called theory of mind. So it means that we're gonna infer what other people are thinking. Right? So we think about what other people are thinking, and we can go deeper into that and try to infer what other we're thinking about what we are thinking. Right? We can go on and on with that kind of recursive mental travel. So theory of mind, as I mentioned earlier, it fit into the picture nicely with the basic component of system 1, system 2 memory. And then given all the four components, we can have the fifth component of theory of mind that perform the recursive reasoning. What was the main difference between the standard question answering and the recursive reasoning in the setting of theory of mind? So in standard setting of theory of mind, we have the people who ask questions saying that, oh, I'm going to ask a question about what I don't know, right? And the answer is saying that I will answer what I know. Right? So that's a very straightforward setting. But in practice, it's not that straightforward because the people who ask questions may think that I'm going to only ask questions that I think they can answer. Right? Otherwise, I would not ask that silly questions. And people may think that, oh, this is maybe that what I think they want me to answer, right? Straightforwardly. But the other person may think that, oh, probably I will answer only what they think I can answer. Right? So that's kind of like try to read other people's mind before doing something. Right? And then that's very, very powerful mechanism because that we need that kind of reasoning to function socially. Right? Without that, the world is going to be very, very boring because no one knows exactly what other people intend to do, or there is no real intentions. It's just a simple fact. Right? And here's one example of the what they call the social dilemma. In the game called Stack Hunt game. So in this setting, that we have the stacks, which is the big animals, and we have the rabbit, which is small animals. And to capture rabbit, and in theory that anyone can do it by themselves, but to catch the stacks, we need the collective effort. Right? But the problem is that because the rabbit's easy to catch, and if you catch rabbits and it make noise, so that the stack will run away. Right? So if anyone trying to optimize for their own benefit, then probably we don't have the very good reward, which is stack. And to be able to capture the stack, we need to step away from the short-term rewards and try to hunt for the bigger one collectively. Right? But the problem is that someone can be selfish. They'll say, oh, how about I would do the rabbit only, because catching stack require a lot of effort, and there's no certainty that I can do it. Right? So if someone like give up their own opportunity for the better gain, then probably they would lose it because of the selfishness of the other member. So in our setting, we try to to put it in a concept of what we call the view aversions. It means that you feel bad if you think, not necessarily the truth. If you think that our action gonna hurt the other people, right? Just through thinking only, no real observation yet. Right? So that kind of high level thinking about the other people, to putting us into the other people's shoes, to think about what we do that may cause some consequences that other people may suffer. Right? So that's called the guilt aversions. And given that, we build a model called the Tomaga, right? And that's quite interesting model that can do the second order theory, saying that what about the other people think what I'm doing, right? So that's very, very interesting. All right, so that was one of the works that we did for the Hookin. There was a paper there. The other more interesting work is also it's called the machine theory of mind from DeepMind researchers. So they tried to build a model so that we can infer what other people doing through the concept of the character networks, which is about the past behavior of the agents, and the mental network, which is about the current behavior, and state, which is observations. So putting everything together, they have what they call the machine theory of mind, and it's been proven that it works very well. To infer the goal and the actions and what's next, for in terms of states for the agent we are observing. So for those who are keen, please have a look at the paper. But then this architecture doesn't have the concept of memory, so we didn't know the real the current context in what way related to the past context. So if we just try to infer it, probably we would miss something, right? So if the context already changed or only one of the specific contexts, then we need to find a way to retrieve the right context for inferring what people may think, right? So that this is one of the proposal that we put forward, trying to infer the trait of the other persons, and infer what other people may think, right? And we also use attention mechanism and memory to enable this theory of mind architectures. So it's been quite long for these two part of lectures, so I'm gonna stop here for a while for the question before we move on to the second part. Any question, please? Okay, if you don't have any question, then I would suggest we take about 10 minutes break before we move on to the second part of the lectures. So we return in 10 minutes. For those who have questions, please give it in the chat if you have any. So we try to answer it later.